So, we will begin the lecture. Of course, in a course, I mean in one course you cannot cover everything of plates and shells. So, we have just tried to uncover, just give the basics of both plates and shells. This has been our aim, and then I have also given you how refined theories. One is the basic theory of both plates and shells, that is the original theory developed by the Kirchhoff and Poisson in the case of plates and Love in the case of shells. That is, they gave the complete equations. And then I have also told you that how to develop improved or advanced theories, which include whatever was neglected in that in the basic theories. And what was neglected? Transverse shear deformation was neglected. That means transverse shear restraints. See, shear restraints, transverse shear restraints and shear deformation mean the same thing. Okay. In Russian literature, they instead of restraints, they use shear deformation. Okay. So, it is the same. So, transverse shear restraints are neglected, transverse normal restraints are neglected. So, because we say the thickness does not change, so transverse normal restraints are neglected, and transverse normal stress is assumed, not neglected, assumed small compared to other stresses. Sigma z, transverse normal stress in the plate and shell space is assumed small compared to other stresses. This is, so we do not exactly put it equal to 0, but it is compared to other stresses. Whenever you have an expression which has addition of some other stresses and transverse normal stress, we neglect this compared to other stresses, because the ratio will be small. So, this has been the assumption. So, one was that how to, because when the thickness of the shell becomes moderately thick, then the transverse shear strains become important. Transverse shear energy become important. Because of transverse shear restraints, you have the transverse shear energy. Energy is what? Product of shear stress multiplied by shear strain into volume, into dV, integrate over the entire volume, you will get the shear strain. So, shear energy is neglected. So, transverse shear energy becomes important first of all in thick plates and shells, even if it is isotropic. Whenever thickness increases, the transverse shear energy has to be included, which was neglected. So, that is why we always stress that whatever has been developed in the first basic theories is meant only for thin plates and shells. Second, later on, you see, there has been lot of developments in materials and in the application. So, you will find that shell no longer or plate no longer is used as a homogeneous isotropic material, one single layer, a single layer of thickness. In many applications, for example, multi-layer pressure vessels, even if you go to Larsen Toubro fabrications of here in Powai, they manufacture lot of vessels where the plates which are there, which they normally bend in the bending machine, it does not consist of a single plate, number of plates which are glued together, joined together, multi-layered construction, so that we can use the material properties more effectively. You know that how does stresses vary through the thickness. So, if you can put some weak material in the central zone, this is what is the idea. You can include, because bending stresses are maximum on the top and bottom, near the top and bottom surfaces. Central zone is subjected to smaller, while shear is maximum, shear stress becomes maximum at the near the middle. So, you use some material which are weak in tension and compression, bending tension and compression, and strong in shear energy. So, like foam, like rubber, there are so many material, honeycomb material, they are there. So, we can have two sheets, and in between you can fill it with something, and then this total can be treated as one thick beam, plate or shell. Now, the moment you take this, now material properties are changing. So, the only place where the change occurs in all this is through the thickness, that integration. When you find out the integrated forces, integrated stress resultants, because in any plate or shell theory or beam theory you have stress resultants, is it not? Instead of stresses you have stress resultant. No theory can give you stresses directly. No plate, beam, shell theory can ever give you stresses, because you are transforming the problem to 2 dimension or 1 dimension. So, they can give you only moments and shear forces. Then it is up to you to find out how to find out stresses. I think there is some relationship. How to find out means, yes, there is a relationship which relates displacement at any point P with the displacement of a point P naught at the mid surface. There is a relationship. So, you can find out displacement. There is also relationship which strain at any point P in terms of the strains at any point P naught, which is. So, once you find out these quantities, so strains are found out, then multiply by Hooke's law, material constant. Once strains are known, strain multiplied by C, C means that constant of material matrix. So, you can get stresses. In theory, we can always get stresses via constitutive relation. Of course, there are some problems that I will not tell you. Problem occurs when you have to find out the transverse stresses. Only for transverse stresses, that means transverse means sigma z, tau x z and tau y z. These 3 components, if the layer is not one, if it is a multi-layer, so at the interface 2 layers where they are meeting, at interface the stresses must be same. This transverse stress sigma z here, sigma z here. Although the material properties are different, they must be same. While if you use Hooke's law, they will come out to be different, because strains will be same at the same point. At an interface, which is a unique point, interface means what? Junction of 2 layers. So, strain will come out to be the same, displacement will come out to be the same, but when you will go to stress, you will find you will get 2 stresses. Why? Because below the point there is a one material, above the point there is another material. So, which is not possible. It is possible for sigma x, sigma y, tau x y, they can be different, but not sigma z, tau z x and tau z y. These are called transverse stresses. These are also called interlaminar stresses. Once you are dealing with laminated system, they are called interlaminar. Interlaminar means between the layers, the stresses that exist between the layers. What are the stresses? Sigma z, zx and zy. So, these stresses cannot be found out using constitutive Hooke's law. It will be erroneous. So, for that we use another method, we call it, we integrate the equilibrium equations. You have got elasticity equations, equations of 3 equations of elasticity in elasticity, theory of elasticity, 3 equations of elasticity. So, we integrate those equations and from there you find out these stresses. So, that is a different story, but otherwise you can always find out in the second phase. We always say first phase you will get displacements of the reference, displacements of any point on the reference plane, and you will get all the stress resultants which are defined at the reference plane after analysis. Then If you want any other displacement, you have to use your displacement field. If you want to find out any strains, you have to again go to your relationship. And if you have to find out stresses, so part of these stresses can be found out from Hooke's law. That means sigma x, sigma y, tau x y can be found out by using Hooke's law. But the other three stresses, if it is a laminated system, they have to be found out from integration of equilibrium equation. So these are, so as you go along, there are many issues, and but then slowly and slowly, our aim, what is the purpose of research? To find out what are the limitations, what are the lacunas in existing formulations, and try to remove those. So that is how research develops, and that is how this subject also has developed. And still there are hundreds of problems that are still unresolved. It is not that all the problems have been solved. There are many problems that need to be solved, especially in the case of shells, because shell is a difficult, equations are complicated and solutions become extremely difficult if you try to find out analytically. Anyway, so for axisymmetric shell, we have found out that the equations are one dimensional. It is only a function of one meridional direction x, and since they are ordinary differential equation, you can find out some solutions, and that examples I have given you, but not many, but certainly you can find out some solutions. Similarly, for open cylindrical shell, again you can find out solutions. Exact solutions have been obtained by many open cylindrical shells and supported on the two curvilinear edges, this side and this side. So, if it is supported here and it is curved like this, you can find out the solution. So, I have told you, please derive the equations and try to see how to, it is given in many books, solutions. Okay. Now, I just wanted to touch upon, then I have also introduced temperature stresses, thermal problem. I think only Hooke's law changes, nowhere else, nothing. In fact, lot of people solve these days hygrothermal. Hygro means hygro, water, water ingress, effect of water. There are many materials, see, listen, there are many materials which get affected, which swell or contract when they come in contact with water. Mostly they swell, swelling takes place. So, you want to study what is the effect of water, I mean moisture, what is the effect of moisture on the behavior of shell if it is made of those material, like a polymer composite material. Polymer, if moisture enters into it, then something happens to the material. So, if you want, so it is called hygrothermal effect. Now, that also comes, effect of that can be put only in the Hooke's law. It enters only at the Hooke's law level. Rest of the things remain the same. So, what I am saying, there are many problems that can be tackled, but everything is a new thing, and it has to be done properly, and people are doing it. So, hygrothermal effect is one, thermal effect is another. Then there are three types of analysis that normally one does for any structure. One is statics, under which in mechanical engineering we call steady state behavior. Statics, solution does not change with time, that is called statics, that is also called steady state. Second one is free vibration. You vibrate, if it is elastic, so you just fix this cantilever beam, you displace this and then leave it. So, you will find under vacuum this beam will keep vibrating. So, you want to find out the characteristic of this kind of behavior, that is called free vibration. There is no force acting on it, but then you have simply you have initiated initially and then. So, free vibration. Then similar thing also happens, if you want to study under compression, anything just like behavior of a column. Why do we study column separately? See, we study beam and then column separately. Column means the moment I say column means that member, longitudinal member, is subjected to compressive load, not tensile load. Tensile load there is no problem, but under compression there is a problem, because instability takes place. At some load, column suddenly collapses, and that is very critical. So, that is called critical load or buckling load. So, that problem also can be described as a eigenvalue problem. So, it is similar to free vibration. And third type of problem is time dependent problem. Any body, you only have three types of problems. One is statics, second one is eigenvalue, and third one is time dependent. Time dependent means if you transient, if you forced vibration, if you have you bring in some machine and put it, attach it, and then you want to study the behavior of this, then it is forced. So, it will be time dependent. So, time dependent, that means as a function of t. So, one dimension increases, space you are having x, y, z, and one t also comes. So, every point will have a displacement as a function of time. So, there are many problems in these areas also. We are covering only statics here, free vibration. I mean, there are so many time dependent problems can be solved of this. Then you see, I think we'll agree that the equations of shells are difficult mathematically. They are complex and tedious, and many people they ran away from shells because of these equations, because these equations turned out to be too difficult for them to. So, there was a time when people tried to simplify. They said, after all, a shell, the bending effect is felt in a very narrow band under root r into h from the edges. Rest of the shell is subjected to only membrane action. See, normally you have both membrane action and bending action. Bending means bending moments M1, M2, M1 to Q1, Q2, 5 quantities. I mean, yes, M1 to 5 quantities. And then membrane is N1, N2, N1, 2, 3. So, you have all these 5 plus 3, 8 quantities which are I mean, I am talking of thin, where they are equal, N12 equal to N21. So, they are and plus in shells you have found out, in plates they are separate. For isotropic plate they are separate. Membrane, if you apply a membrane force, it will not cause any bending. If you apply a bending moment, it will not cause any membrane action, but not in shells. Shells, all the equations are coupled. There is M also, and in the same equation N also is occurring. So, they cannot be separated. So, what this most people felt that for solution, when it comes to solution in the early 20th century, because 1888 the equations came, then early 20th century, people, because they wanted to solve, no computers were there, the only alternative was how to simplify the equation. Then they classified, they said, can we not think of, why do you have to study bending of shells? do you have to all the time study bending of shell? Bending means complete, bending, membrane combined. Do you have to all the time study membrane and bending combined? And this was found out, that solution was available. I have also got the solution now, that the bending effect is, they are all localized. Wherever supports are there, it is in the vicinity of the support, effect of bending moment. Wherever loads are there, concentrated loads, there will be bending moments. Away from this, the shell is mostly in membrane action. They say, then is it so important that we should study combined? So, many people said, let us now classify two kinds of solution methods. One is membrane theory, simple membrane theory of shells, and other one is membrane and bending combined. So, they tried to get approximate solution of shells using what is called membrane theory of shells. What is membrane theory? That I will tell you today. Membrane theory means you have to suppress the bending effect, but then the solutions will not be valid in the entire zone. That also must be kept in mind, or you have to devise the boundary condition in such a way that it does not introduce bending stresses in the shell. That means, the boundary conditions have to be devised, or if you are not able to devise the boundary, then what will happen? There will be extra bending near the support, and designers see, that approach is approximate approach. Designers say, okay, if there is additional bending near the, I will put something, I will deal with it separately, put some other, some further reinforcement, I will increase the thickness of the shell near the boundary, but let the entire other portion be designed from membrane theory of shells. So, one is called, there are two available methods for determining state of stress in a shell. The first one is called the exact method, or which constitute the bending theory or bending membrane theory, approaches the problem in its entirety, no approximation. This takes into account both forces and moments and the resulting deformations. Then there is a second method, that is called simplified method, which constitutes the membrane theory or momentless, we also call it momentless theory, and that assumes that owing to the very small thickness of the shell compared to the other dimensions, bending and twisting moments cannot occur, and equilibrium equations involve only the membrane forces in the tangential plane of the shell. So, I will give you a simple how to develop bending theory of shells, then you do not have to worry about So, how do you deal with membrane theory? It is not a theory, membrane equations or something, but then it is literature, it is called theory, membrane theory of shells. Because this comes out of. So, idea is here the bending, all the bending moments, shear forces, they are neglected, and we assume that the shell element is subjected purely to only membrane forces. So, I will just take you a example of a cylinder. So, normally you will have a cylinder so I can take an element from this cylinder and in this direction it is making an angle phi x phi, no, phi this side, phi this side, phi measured from here. So, you see this is dx and this is r d phi. So, what are the forces that will be acting on this? This element, if you say that yes, it is subjected to some kind of forces in the, let us say there is a p x p phi and p n is upward. So, load is p x, p phi and p n per unit area. N is normal to the surface. So, this element, if you take it out from the total shell, then will be subjected to, this is a positive phase and this is again a phi positive phase, this one is positive. So, let me show it, this is negative x phase. So, first show me, I will show it on the negative x phase. So, there will be n x, is it okay? Negative x direction positive and negative phi direction, there will be n x phi. Is it okay? N x phi will be like this, n x phi. When you go on the positive phase, there will be n x plus some increment d n x into this, and then n x phi delta n x phi by dx into dx. In the phi direction, this is the negative phi. So, there will be n phi and there will be n phi x, negative x direction, n phi x and n x phi are same in the case of thin shells, and when you go to the positive. So, there will be n phi plus there will be some d n phi by d phi into d phi, and then there will be positive x. So, this one will be n phi x plus d n phi x by d phi into d phi. So, that means the entire load, we are assuming that the entire external load is resisted by these internal forces. This is one element which is in state of equilibrium. Our coordinates are x phi z, right handed screw system. Is it okay? Element is okay. So, we are assuming that the entire load is resisted by only membrane forces. Of course, this will be possible only first of all away from the supports. So, somewhere far away from the supports, it will be in membrane state of stress. So, if it is so, then we can derive from first principle. We need not go to curvilinear coordinates. Of course, from there also you can derive, you will get the same thing, but here one is phi. I think this, see, this phi is there and this phi is here. And then this will be supported by P n normal load, because they will be downwards, they will be radially downwards. So, we can take that. So, it is possible to write n phi, the three equations, and I will not go. So, n phi can be written as n phi P n r. R is the radius, capital R is the radius of the shell. Then x phi by dx minus 1 by r So, you can write down equilibrium equation in x direction, equilibrium in phi direction, and equilibrium in n direction, normal direction. Three equations we will get, and these are the three. Let us not spend too much time on how they have been derived. Of course, it is possible. For example, n phi multiplied by this dx will be the total force here. Here again, this is the incremental force. This n phi will be okay, and then you write down, it is possible you have to take the forces like this. N phi, see n phi will be, because n phi is here and one n phi plus increment on this side, n phi plus delta, delta n phi, and this is all your P n, and of course, length is x. So, if you vertical equilibrium, because this will not enter, this will not enter, this will not enter, this force will not enter, if you take vertical equilibrium only. So, it is possible to obtain this, the first equation, P n into r, this is r. In fact, this is d phi by 2. We can take, and then angle is small. So, we can take sine and that approximation. So, it is possible to write down these three equations. This one is simple in x direction, and x direction is simple, that can be written without much difficulty. Phi direction slightly you have to spend little time. So, this is the three equations. Now, you find that there are three equations and there are only three unknowns. So, three equations three equations have only three unknowns. And what are the three unknowns? It is n x, n phi and n x phi. So, problem is statically determinate. Somehow we should be able to solve only these three equations in order to get all the three quantities. Now, if you take n x phi, so if you, how do you get n x phi is equal to minus integral p phi plus 1 by r dx. Second equation I have taken, and plus there will be some constant of integration which will be a function, because you are integrating with respect to x. So, it should be a function of phi, some function of phi, which is this is a constant. After integration it must be, if you differentiate this with respect to x, so this will be 0. Similarly, this one you can integrate, you will get n x will be equal to minus p x plus 1 by r plus some, this is also with respect to x only. So, the function f 1 must be determined from the two boundary conditions. So, f 1 f 2 can be determined from boundary conditions x equal to 0 and x equal to L. Length has to be, after all you are moving in. I hope so. X equal to, na? It will be x, no, phi. Yes, x equal to, yes, you have to specify one end of the shell and the other, yes, each of the profile forces given and phi. If now, I have a simple solution here. That is why many people say that shell is a theory of differential equation, but it is not a simple differential equation. It is, we should not teach this as a course in mathematics, but it turns out to be mathematics. I mean, we have to understand that yes, we are solving a problem, not it is not a fictitious mathematical problem. So, let us assume now solution. I will just try to give you a simple 0, 3. A particular solution. See, it is cylindrical shell. Cylindrical shell, theta is closed, phi is closed, phi. So, there is no boundary conditions to be applied there. That is what we are solving. We have taken an element from this. although I have shown. So, we have taken an element from here, this element we have taken and we are writing. So, solution for this, let us say that there is no, we are not applying any load in. I mean, again I am simplifying, so that and P phi and P n, P phi, yes, P phi means tangential, yes, load, tangential load is independent of P phi and P n. That means, still it can be non-symmetric load even in this, because P phi will give rise to non-symmetric load. If P phi is present, yes, it is not axisymmetric. So, if P phi and P n are independent of x, then your equation here, now let us see, independent of x. So, if P phi is independent of x, yes, so this will integral will only dx will be, so dx will become x, and what about the other one? So, what about nx? Nx also I have got nx px is 0. So, 1 by r, this is okay, and I think let us see, because while solution you just do some something manipulation, so that it comes in a particular form. So, in that case nx phi, the first one, nx phi here, nx phi, where is nx phi? This one will become nx phi equal to minus P phi plus 1 by r d, d means it is d n phi by d phi, yes, independent of x, independent of x, solution becomes independent of x. So, it will be d n phi by d phi bracket into x plus f 1 phi. So, it is the same, this is all. Only thing you have to note that this is what will happen if, now put or say some function f phi is equal to P phi plus 1 by r why it is done, that because people have solved this problem and it helps. So, therefore, your nx phi is equal to minus x f phi plus f 1 phi. Okay, so, this is 1, and what about nx? Nx equal to 1 by r here, Px is 0, 1 by r nx phi, yes, dnx by d phi. dnx phi by d phi. Should it be ordinary or ordinary? D phi into dx plus f2 phi, and that is equal to integral 1 by r. हाँ, ये जो है this is 1 by r from the first one derivative of this, it is derivative nx phi na. So, derivative of this, so it is derivative means x into minus x into d f phi by d phi by parts plus x equal to 1 plus just d f phi and that comes out to be equal to x. Integral is with respect to x, this is a function of phi, so it will become constant. So, x is square by 2 r, yes, minus minus plus x is square by 2 r d f phi, yes, it is okay. See, this is a function of phi. So, function of phi dx. So, as a integral is with respect to x. So, it will be only x is square by 2. So, this will be like this minus this minus will come here minus. So, minus d phi of phi plus करता हूँ ना, next one. nx phi क्या है वो तो यहाँ डिफरेंशिएट किया ना, तो इसको डिफरेंशिएट किया nx phi को एंड तो ये यस. सो दिस इज this second term is why it is wrong? No, here this is a product of nx phi equal to x into f phi. So, no, then this is a partial derivative then. Then f1 also is a function of phi. F1 also is a function of phi. Acha, F1, yes. Sorry. That is right. So, this is I have made a mistake. I think here I should have written this is F1 phi, small f1 phi, d f1 phi. It is okay, f1 phi dx, ठीक है, plus f2, okay. It is ordinary only, yes. F1 phi only I made a mistake there. So, this is x square by 2, this so far it is okay, and then this one will become x by r d f1 phi by d phi. Plus f2 phi. And of course, the third one is there, n phi is, that is same Pn into r. That is the general solution. Okay. So, the boundary conditions must specify the support which the shell receives along an x equal to constant. This support is usually supplied by connecting this edge x equal to phi. Okay. Connecting this edge, normally what now? I mean, all this is theory. You see shell, this is shell, a small shell. Edge means this is what you will see. Normally, this at the edge you do not leave it just as a thin shell, but it is supported over an arch. That is what I am trying to say there. There will be an arch below. So, if this is a shell here and here, at the end you will have a stiffener. Arch means what? It is acting as an stiffener, x equal to with a ring or an arch or a ring. If it is a complete shell, then you will have a inside at the edge only I am saying, you will have a this is at the edge, a ring. Open shell, this is an open shell. This is what. So, when we apply, this is what I have written a longhand. So, let me just read it. When we apply loads in the direction of the generator, what is it to this reinforced edge? What is a generator? See, if there is a ring, this edge and this edge, x equal to 0 and x equal to L, and if I have a straight line, if I move that line over the edge, I will get the shell. So, this line is called generator. I am generating the shell by moving the straight line over the edge. So, one is called generator, it is generating. So, that is what is it says. The ring, yes, apply the load generator to this reinforced edge. The ring cannot substantially participate in the carrying, cannot substantially participate in carrying them, since it could only do so with rather large deflection, which the much stiffer shell will not permit. We conclude therefore, that if no such load is applied, that is, if there is no nx equal to 0 along the edge, this must be used as a boundary condition out of plane deflection. On the other hand, this is slightly complicated. I have also forgotten what I have written several years ago. So, okay, so this is the idea is okay, let us, I think best thing is to stop here instead of okay. So, we will stop here and